Okay, we are going to start talking about our focus 2. So let me share my screen. What you have to realize is that we're on our way to trying to understand chemical equilibrium. In order to do that, we have to understand the laws of thermodynamics. So I'm going to go through the first, second, third, and 0th law of thermodynamics. The second's going to be the most important, but you can't understand the second law without understanding the other laws. So this focus starts with a lot of definitions, so I'll go through them just so you have them in some notes, and then I'll summarize kind of what I think are the important parts when I'm finished with that. So we're going to be talking about the internal energy when we talk about the first law, and thermodynamics is the study of the transformations of energy. So we're going to start by defining a system and a surrounding. So if we're talking about energy transforming, we're usually moving energy from one place to another. And so we have to essentially define what's the place, our system, and where are we moving it to or from. That will be the surroundings. So your book goes through this, and it just makes sense depending on what kind of system you have. You might have an open system where both matter and energy can flow in and out, so like an open beaker, or you might have a closed system where energy flows but the matter's contained, so like a jar that has a lid on the top but isn't insulated. Or then you can have an isolated system where nothing flows, matter's held inside, energy is held inside. So that's something like a thermos container. So we'll always have to think about our system and surroundings as we go through problems dealing with thermodynamics. So we need to think about the more precise definitions for work, heat, and energy. And we're going to be reading the book, The Second Law. So we're going to get on a molecular level some very fine detail on these terms. So work by definition is done to achieve motion against an opposing force. Energy of a system is its capacity to do work. And heat energy is moved as a result of a temperature difference. So we'll go through understanding these in great detail. Sorry, I don't want to have it too small, but I can't seem to get that in. Okay, so heat and work are both ways to move energy is the important thing to understand. Systems contain energy, but if we want to move it in or out, we either move it through the process of heat or the process of work. So toolkit number 6, you can look over that, but I have the important parts here in the notes. The first is that we're talking about system in reference to our work in reference to the system. So if we're talking about an infinitesimally small amount of work being done, it's going to be equal to negative force times how far you move something against that force. So if we look at force as a dot product with movement, you could move it in 3 different dimensions, the X, Y, and Z. So you can have work in different directions. If we're just talking about one-dimensional work, it will be dW is equal to negative force in the X direction times how far you move something in the X direction. So just a couple definitions. These are always good to remember. A joule is a Newton times a meter, and that's equal in fundamental units to a kilogram meter squared per second squared. A watt is a power unit, so it's the rate at which energy is moved. So you often get electricity in watts, but you could have different energy units, but it's 1 watt is 1 joule per second. So a W is a watt. So you can store energy in a system, and stored energy can either be kinetic or potential energy. And so when you add those two together, you have the total stored energy. The kinetic energy always has the same formula. It's the energy of motion. So it's 1/2 mass times velocity squared. And potential energy is energy possessed as a result of a position in some field. For us, we're mostly going to be interested in the electric field. So if we're talking about, for example, a proton and an electron interacting in a molecule, you'd have a +1 charge and a -1 charge. So the Q's are the charge divided by 4 pi times permittivity, and r the distance between those two charged particles. So when we're talking about potential energy, that tends to be what we're going to think about. You also have our gravitational potential energy and other potential energies. You even have this technically would be the potential energy of mass, so E equals mc squared. So there are lots of different ways to think about storing energy as potential energy. The molecular interpretation of heat and work, we're going to really just skip over the little bit they do in this book. And when we read the second law, we will go into great detail, page after page, understanding the difference between moving energy as heat and moving energy as work. So you don't really have to focus on that in your textbook right now, because we'll be reading those chapters. You've already started. So the definition of internal energy is the potential and kinetic energy that's internal to the system. So for example, if you have a cup of water, it's all the energy of the kinetic energy of the molecules bopping around, as well as the interactions of those water molecules with each other. But it wouldn't be if I threw the cup across the room. That would be external energy. So when we talk about U, we're talking about internal energy. So just that energy, both kinetic and potential, that's stored within a system. It's pretty hard to think about total U, the total stored energy, because like I said in the last sheet of notes, you have so many places to put energy. You have the masses, potential energy, you have all the interactions. So in general, we can measure how much the internal energy changes. So a change in internal energy is the final internal energy minus the initial, but measuring the actual absolute value of internal energy would be a much bigger task. You probably remember this from either 266 or 107, that internal energy is a state function and it's an extensive property. So more stuff, more internal energy. And state function means it's independent of how you got to where you are. So we looked in the first focus at the ideal gas law to use as an equation of state. So a state that, or an equation that defines the state of my system. So for example, if you have a gas at some pressure, volume, and temperature, it has the same internal energy regardless of how it got there, how you created that pressure, volume, and temperature relationship. So the molecular interpretation of the internal energy is that we can store energy in translational motion, rotational, vibrational. There are all the potential energies of interaction. So all of that energy, either of motion or how particles are in relation to each other, therefore how they are in a field, gives you their potential energy. So we have a contribution from each mode, and this equal partition theorem is something that you can't prove, but it always works. So it's one of those situations where it's logical and it works. So for a sample at thermal equilibrium, the average value of each quadratic contribution to the energy is 1/2 kT, Boltzmann's constant, times temperature in Kelvin. It's not always valid for vibrations because vibrational energies are so far apart that often you can't excite those energy levels at a low temperature. And so equal partition theorem is valid for translational and translational under most conditions, but not always for vibrational. And we'll look at what that means and how you'd even use that relationship as we go on and put some of these definitions into more concrete examples. So the internal energy of a perfect gas is independent of the volume it occupies. It only depends on temperature. We're going to talk about that a lot, but it's extremely logical that if you have a sample of gas, and if you call it perfect, then all you have is kinetic energy. There's no potential energy because the perfect gas law says that this particle doesn't see another particle, doesn't even know it's there. So if I expanded that container you aren't changing the interactions in any way. There's no change in potential energy of interaction because you said the potential energy was equal to 0 when you said it was a perfect gas. So we'll see, and that will be a very important thing to remember, that it only depends on the temperature, and the temperature will determine the velocity and therefore the kinetic energy. So really what you're saying is the internal energy of a perfect gas only depends on kinetic, or yes, on kinetic energy and not potential energy. So for us, summary to this point is that internal energy is the stored energy within a system. It can be potential energy and kinetic energy. Kinetic energy's formula is always the same, 1/2 mass times velocity squared. Potential energy depends on what kind of field you're talking about, gravity or others, but for us, it's mostly going to be the potential energy of charged particles. Q1 and Q2 are the charges on those particles, divided by 4 pi permittivity of a vacuum times the distance between those particles. Heat and work are ways to move energy. So when you use them precisely, you would want to say, this is the quantity of energy that moved as heat. This is the quantity of energy that moved as work. They're not types of energy that's stored. They're just ways to move energy. So with all of those definitions, now we can think about the first law. So the first law of thermodynamics says that heat and work are equivalent ways of changing the internal energy of a system. And the first law states that the internal energy of an isolated system is constant. Or if you state it mathematically, if the internal energy is constant, if the internal energy changes for your system, you have to be able to measure where that energy came from or went to. So energy either had to flow from the system as heat or work. So that's a statement of the first law in mathematical terms. So that means that if you're talking about an infinitesimally small amount of internal energy change, that's equal to an infinitesimal amount of energy moved as heat or infinitesimal amount of energy moved as work. So first we'll go through how would you identify that work was done. So we're going to need to be able to measure all of these things as we go along in order to understand where equilibrium is. So this may seem very abstract, but this is a long lead up to understanding, it's in chapter 6, what chemical equilibrium is. So 5 chapters are focuses on understanding equilibrium. So if we talk about work, we're mostly going to be talking about expansion compression work where you have a change in volume. So for example, if you have this cylinder and you put a frictionless piston in here with some area, if the pressure inside is greater than outside, this is going to go up until the two pressures match. So until you reach what we'll call mechanical equilibrium. So if you move this piston some distance dz, you'll be doing work. So dw would equal negative the value of the force. The force is going to be related to the pressure, we'll see, times how far you move that piston against that force. So pressure is force per unit area. So we'll be able to see how we can get a force in here in terms of properties of the gas. So dW is going to be negative pressure times area. So pressure times area is force, and we want force, times dz. But area times dz, so the area of this piston times how far you move it is how much you change the volume. And the important thing to realize is work is always against an external pressure. So when you talk about this gas working, it's doing work against the external pressure. That's the force pushing on it. So it's always the external pressure that goes into work. For example, if this was 0, if you were expanding this against a vacuum, then you wouldn't be doing any work because there'd be no force pushing down. So we need to integrate this to get the total work. So integrate dW and you get W, and we're going to integrate from V initial to V final over pressure external dV. And depending on what kind of system and surroundings you have, that pressure external will take on different values, and you'll have to think carefully about how you integrate this. So the first one is if you do work against a constant external pressure. So this is just in, for example, this room, and the piston is going up against the pressure of the atmosphere. Then I can pull pressure external out front, and I'm integrating, oops, there should have been a dV there. I'm integrating over dV. The integral over dV from V initial to V final is just delta V. So you end up with negative, and that should still be P external times delta V. So let's just look at a quick self-test. This is self-test 2A.1 on page 40. Tells you you have 50 grams of water and it's undergoing electrolysis. So if you start out with liquid water, you're going to make hydrogen gas and oxygen gas. You're going to make 1 mole and 1/2 mole. So it wanted us to calculate the amount of work that would be done if we did this work against a constant external pressure. So work is going to be negative P external delta V. Delta V is going to be volume of the gas minus the volume of the liquid. Should be an L. And so the volume of the liquid is pretty much 0 relative to the volume of a gas. So we can approximate this to be just the volume of the gas, this delta V. And so the volume of a gas, if it's perfect, so I'm going to say it's perfect because the problem told us that, then volume of the gas is going to be nRT, pressure external. So it's going to stop expanding when its pressure equals the pressure external. So I calculated that we started out with 2.78 moles of water, and we made 1 mole of hydrogen and 1/2 mole of oxygen. So that gives us 4.17 moles of gas. So if I put that into the work expression, negative P external, this is delta V. So delta V also has pressure external in it because that's the pressure the gas will end up at. So we don't even have to know what the pressure external is. It's going to cancel. And so work is going to be negative nRT. So we have 4.17 moles times the gas constant in joules per K mole times the temperature they gave us of 298. And we only have 2 sig figs, so our work is going to be negative 10 kilojoules. So that's one way to do work. Another way to do work is in a reversible way. So this way, when you say it's against a constant pressure, it's irreversible. Those are basically the same situations. And so when we do reversible work, we want to do it in such a way that at any point we could reverse whether it's expanding or compressing by just an infinitesimal little change in the external pressure or internal pressure. So we start out with our same definition of expansion work, but if it's reversible, this is the important part. We need the internal pressure, the pressure of the gas, to be equal to the external pressure just about at all times. So if it's expanding, the pressure of the gas will be just a little bit more. And if it's compressing, the pressure of the atmosphere will be a little bit more. So depending on which way it's going, but to be almost equal to each other. And then when we look at integrating it to get a total quantity of work, we have to think about the fact that the pressure of a gas depends on the volume. So we're going to have to know that relationship in order to integrate the right-hand side. So if it's a situation, we need to put some restrictions so we know how to integrate it. If it's an isothermal reversible expansion of a perfect gas, then we know that the pressure of the gas is going to be nRT over V. But if it wasn't isothermal, I couldn't integrate this because T would be changing and V would be changing. So if it's isothermal, then temperature is constant. It can come out front of my integral, and I'm integrating 1 over X essentially, so dV over V, which is natural log. So our expression will be negative nRT ln of V final over V initial. We'll use that equation a lot. So just want to make sure that you always are reminding yourself where the equation came from. So that's isothermal reversible expansion of a perfect gas gives you that equation. So if we look at page 41, there's an important thing to think about in this graph. So it will always be true. So when we look at this graph, this is the graph of pressure versus volume. And so it's the integral, it's work essentially, because it's the integral of P dV. If you're doing it reversibly, you're always going to have a little bit more work, because when you think about it, if you expand a gas against a constant external pressure, which is equal to its final pressure, the two end up at the same place, but the area under this bottom tan curve is less than the area if you include the top part. And if you think about it, it's really because right here, you're doing more work. You have the ability to do more work because the pressure of the gas is much, much higher than the pressure of the atmosphere. So that means you're essentially wasting some of that pressure difference. So we'll think a lot about the fact that a reversible process is always a limit. It's a limit of how well you can do. So you get the most amount of work if you do a process reversibly. So now if we also want to think about total internal energy changes, we have to think about how would you measure heat transfer. So dU, change in internal energy, is dQ plus dW for expansion compression, plus you might have other kinds of work too. So ADD just means additional kinds of work. Maybe it's a chemical system, you have electrical work, or maybe you have work from surface tension. So that's any other work that wouldn't be P dV. So when the additional work equals 0 and V is constant, then there is no work. So if the volume doesn't change and there's no other kind of work, then dW is 0, and that means du equals dq, and the little v means that's only true if the volume is being held constant. So if you have a finite quantity, delta U equals QV, and we would use calorimetry to measure Q. So Q is equal to the heat capacity times delta T. You can also change the temperature or add heat with like an electrical heater. So if you have an electrical heater at some current I, and you pass that current for some time T through a potential difference, then you'll be able to also measure that as a quantity of heat. That's a common way to measure the heat capacity, because if you have this and this, you can measure the heat capacity of the system. So the heat capacity, by definition, we're going to have to worry about two different heat capacities now when we're talking about gases. One where you add the heat at constant volume, and one where you add the heat at constant pressure. So a constant volume heat capacity is, by definition, the partial derivative of internal energy with respect to temperature, holding volume constant. So that's a definition that we will use. And you should go ahead and read the Chemist Toolkit 9 on page 44. It just reminds you what it means to say you're taking a partial derivative. It really just means you're taking the derivative with respect to one variable and holding another one constant. So it's not any more challenging, but it'll show you in pictures on page 44, just kind of reminding you what that means in a visual way on a graph. So if we look at this definition, this means that if we want to measure an internal energy change, it's the CV times delta T. Just move the delta T over to this side. And then we'd have to integrate the right-hand side to get delta U. If CV is constant, which it isn't always, but if it is, you can pull it out front and you come up with the equation that delta U equals CV times delta T. So you can always measure an internal energy change if you can measure a change in temperature. Okay, so I'm going to stop there, and the next section will be defining a new function, enthalpy, but I think I'll do that in 2 different lectures.